So in this talk, I'll try and go over the basic philosophy of singlet NMR experiments and hopefully explain some of these principles in a way that makes anyone who hasn't tried them yet more curious. So you can't really talk about a singlet NMR without talking about relaxation. And eventually, any kind of a physical configuration you prepare is going to succumb to entropy. And NMR, by definition, no matter what kind of NMR you do, is the science of preparing and reading out non-equilibrium order in nuclear spin ensembles. And in general, you can have different spin order configurations, and all of them may have distinct relaxation behavior. And it is possible to experimentally access them. And by doing differential relaximetry of, let's say, all of the different spin orders you can access, you can gain more knowledge about the dynamics of your systems. But let's say I'm guessing that most of us will be familiar with the relaxation of longitudinal and transverse order by T1 and T2. But let's say recent developments in things like long-lived order, which is a very general blanket term, and specifically a nuclear singlet order, have a lot of exciting prospects. So let's just mention times when you want to have relaxation, in which case I will be of no help to you. I'm sorry. So if you want faster relaxation and less time between scans, then you probably don't want singlet order. And let's say this is not often appreciated, but some of the very first attempts, people who were looking for NMR signals didn't succeed because their relaxation times were so long that they ended up saturating their systems and never finding the signals they wanted. And rarely do people ever say that Bloch and Purcell were actually acutely aware of these issues and actually took measures to prevent them. So one of those groups actually put some paramagnetic salts in their water samples, specifically to avoid the saturation. And let's say some cases you want longer timescales, because spin ensembles at the end of the day, they can hold memory, they can hold configuration. And if that memory is precious, like let's say, for example, hyperpolarization, there's been a lot of interest in techniques like DNP, parahydrogen optical pumping. If you have hyperpolarized spin order, you really want to keep that. And unfortunately, it's a limitation for, let's say, medical applications. That's nuclear relaxation times are so rapid that that's hindered applications. So having long-lived spin order is something that is very needed in this area. And here is just an example of what a long-lived singlet order can do in some of my experimental results. So these are 13C spectra. And these were actually generated from a thermal equilibrium magnetization, room temperature, solution state. That's at 9.4 Tesla. And you can store that polarization as singlet order at 1 millitesla. And it turns out that you can preserve all of this magnetization one scan after 100 minutes of storage, which really opens the path to a lot of crazy NMR. And here is just a very basic diagram, which in general is how every relaximetry experiment goes. Doesn't matter if you're doing T1 or if you're doing TS. No matter how complicated it seems, at the end of the day, it's just this. There's a polarization or equilibration step at the beginning, where you may polarize your system at a high field magnet. And then you prepare an equilibrium order For the sake of simplicity, I've just put Zeeman order here. And after that, you have a specific generation sequence to generate whatever kind of order you're interested in. You let that order evolve for a certain while. You may do some manipulations to it. You may change some things, change the field, for example. Then after that time is up, you still have some of your target order left. And you read out how much of it is remained in an acquisition step. And really what we're going to be talking about here is these steps about generation and readout of these very interesting spin order configurations. And just to get it out of the way, let's say what a long-lived operator is. Very loosely, you don't even have to give a formal definition at this point. It's any operator representing a special configuration of nuclear spin states, usually a population difference, emphasized between states of unlike permutation symmetries. And let's say long-lived order must be invariant or significantly invariant or relatively invariant under some relaxation superoperator. And the most common example, a very classic one, is a singlet order in a system of two spin halves under the action of in-pair dipole relaxation. In proton spin systems, for example, this is the dominant relaxation mechanism. But if you have a singlet order in a proton spin pair, then that relaxation mechanism no longer has any contribution. And Abraham actually discussed this in his very old book. And there's a very simple argument for it. The singlet state is an anti-symmetric state, and it can't relax under symmetric perturbations like dipolar relaxation or in-pair dipolar relaxation. And let's just go through these very classic, very basic prolaximetry experiments just to get our philosophy in there. The inversion recovery experiment. The generation sequence is a very simple inversion pulse. You generate inverted longitudinal order and you read it out at a simple 90, that's it. And what do you get? You get a T1 as a function of the evolution time after the inversion pulse. There's also another famous example, which is very well known in solid states NMR, which is the Jean-Eyre-Brocard sequence. And actually, this was a revolution for the field of solid state NMR, because they had all of these fancy methods like adiabatic demagnetization to generate this dipolar order, which everyone was interested in at the time. Which was only later with this sequence that they discovered you could do it with a simple pulse sequence. And it's just this very simple thing. You can generate and read out how much dipolar order you have. And typically it's denoted with this T1D relaxation time. But what we're doing now is something newer. It's about singlet order in liquids. And the question about generation sequences for them hasn't been so straightforward. So it starts, we look at some very basic stuff, which is two coupled spin halves. And we're looking at the case of magnetic equivalence. So if you have a spin half ensemble, specifically an ensemble of two spin half pairs in isotropic liquids, and you don't have any symmetry breaking terms, you get this J coupling Hamiltonian. This is often called an A2 spin system. And the scalar term J12, electron-mediated coupling, corresponds to the splitting between the singlet and triplet eigenstates. And explicitly, you can write them here. This is very basic quantum mechanics. You have the singlet state here, antisymmetric, and the triplet manifold, where the Hamiltonian has these nice energy eigenvalues. And singlet order which is different from the singlet states, I may add, is defined as a population difference between the singlet state and the mean population of the triplet manifold. So you can see it derived here. This is the Cartesian product operator form, and for this reason, it's also been called scalar order. And again, going through these basic properties, the singlet is anti-symmetric with respect to exchange. Triplet states are symmetric, and the transitions between them are supposedly forbidden to first order, unless you have an anti-symmetric term that mixes the singlet and triplet states. And let's say that in true A2 systems, you can't access singlet order by coherent means. Incoherent means is another story. And the golden ticket to any kind of singlet NMR experiments is breaking the symmetry. And if you have a broken symmetry, then you can access the singlet order. But the key to this experiment is you have to impose it later. And here's just some very common examples. Coherent mechanisms which allow you to access a singlet order include chemical shift differences within the spin half pair. This is when you have anything from an AB to an AX system. So any kind of a molecular asymmetry can introduce this term. And you could even have unequal J couplings, aka magnetic inequivalence, to one or more spins outside the pair. So let's say a systems of this type. And in fact, this was pointed out as early as the 70s that it could be a singlet relaxation mechanism or a way to access singlet triplet transitions. But the experiments weren't done until much later. And as for the incoherent mechanisms, usually there's not much you can do about these. They're just inherent relaxation properties. You have out-of-pair dipolar interactions from all of the other spins, and let's say both the molecular spin system and the spin ensemble. You can have a non-coincident CSA tensors, and this was actually also well known since the 90s in solid-state NMR, that these could induce singlet triplet transitions. You could have random fields, and you could have paramagnetic impurities, which is probably the oldest. This goes back to the experiments in the 1920s, where ortho-para hydrogen transitions, and let's say generating para-hydrogen, was done by introducing these paramagnetic impurities at low temperature, symmetry breaking, and then removing those impurities. So eventually you end up with a para-hydrogen, and it's very stable. And it can stay for days and weeks. And let's say what we do now to our very basic model. We take our A2 system and we introduce a symmetry breaking term, which here I've called delta. So the delta term here is an isotropic chemical shift difference. And now it's formally an AB system. And it's convenient to define this nice quantity here, which makes things much more simple, which is this singlet triplet mixing angle, which is basically a measure of how broken your symmetry really is. And as long as you have this term, doesn't matter how small or big it is, you can access singlet order. But the problem is it may no longer be an eigenorder. So here's just an animation here showing what all of these different inequivalence regimes look like. So you can see the singlet triplet mixing angle here. And we're gradually increasing the chemical shift difference in a spin system simulation with a fixed J coupling of 10 Hertz. And you can see us going all the way from pseudo A2, almost equivalent systems, to intermediate equivalents, to let's say, a strong inequivalence. And for all of these systems, you have different solutions when it comes to generating singlet order. And let's say in the Hamiltonian eigenbasis, your eigenstates are going to look like this. They're going to be functions of this singlet triplet mixing angle. And the diagonalized Hamiltonian, again, this is the rotating frame. We're ignoring any huge normal frequency contributions. You just get this. And the focus is going to be between these S0, T0 states in this zero quantum subspace. So to preserve your singlet order, I mentioned before that it may no longer be an eigenorder. You must actually suppress the same symmetry breaking terms that allowed it to be accessed in the first place. And there's a lot of ways of doing this, but to keep this talk simple, let's say there's two main techniques, and these are the two first techniques. There's strong spin locking. And let's say when you have resonance and sufficiently strong spin locking on resonance, on the middle of your two spin resonances, within certain approximations, it suppresses chemical shift differences. That's one way. The second way is to do field cycling. So let's say you start out with experiments at 9.4 Tesla. You go down to something like a millitesla or 10 millitesla or a range of fields. And because chemical shift differences scale with magnetic field, when you go outside the magnet, there's a good chance that it's going to be almost zero in all but the most asymmetric molecules. And let's say one of the nice things of the latter approach is you also remove higher order CSA terms, like rank 1 and rank 2 CSA interactions, which may end up preserving your singlet order further because they can no longer act as relaxation mechanisms. And there's all kinds of borderline techniques, which I won't talk about, like chemical reactions. You can generate singlet order in a molecule, then do a certain chemical reaction such that that molecule becomes symmetric and all of your anti-symmetric terms go away, preserving your singlet order more. And then you can do all kinds of crazy chemistry, but that's not my area. And here we can also define another operator. So we talked about singlet order. And there's this thing called singlet precursor order. It's been given a lot of names, unfortunately. It's been called quasi-singlet order, a name I don't like. It's also been called long-lived eigenorder, to reflect the fact that this operator, which in general is different from singlet order, can also have long-lived properties. So it ends up looking like this. And you will see that unlike singlet order, it's not constant in the Cartesian product operator space. It's a function of the singlet triplet mixing angle, which may change in experiments. However, when it comes to the population space or the density matrix view, it looks completely analogous. And this has implications for the experiments we're going to do. So let's look at the example of spin locking experiments. In spin locking experiments, typically the rise time of the spin lock can be on the order of nanoseconds. And let's say when you're doing a fast symmetrization on singlet order, then your operators tend to remain unchanged. This is what's called in quantum mechanics the sudden approximation, because simply your system doesn't have the time to adjust. So you start with singlet order in the beginning, you end up with singlet order at the end. So the operator you have, I1.I2, doesn't change. What does change is the representation. So let's say this was your eigenbasis, because you have a symmetry breaking term, the Hamiltonian. Then you apply a strong spin lock. Now your spins are to a very loose approximation, chemically equivalent. And now you've diagonalized this. And let's say you don't have these singlet triplet coherences going on. Assuming that, let's say, your spin locking is strong enough, and this is a loose approximation for the sake of argument. And the general scheme of these experiments is going to look like this. So you excite your singlet order. You apply some form of symmetry switch, which I've notated here. This is just simply removing any of your symmetry breaking terms to preserve your singlet order. You let it evolve. Then you reintroduce these symmetry breaking terms, and you read out what's left of your singlet order. You measure a signal. And there's two different, let's say, or two main symmetry switches. There's one that happens with, let's say, the sudden approximation, or some might call that the diabatic path, where you generate the singlet order, you apply a fast transformation like the spin locking, and it stays the same. Then there's another one which fits within the so-called adiabatic approximation, where you generate an adiabatic precursor. You slowly lower your symmetry breaking terms, typically by a slow V0 field cycling. And let's say you end up with something that's adiabatically correlated, which I'll talk about in a bit. So going back to the spin locking experiments, the way this was first done was really designed for one type of spin system, which was the AX strong inequivalence weak coupling. And let's say the first pulse sequence used to directly generate singlet order. This was actually our second paper, not the first one, but it was the first one to directly generate singlet order. Was this pulse sequence here. And as you can see, it's very simple. The parameters are basically a J-synchronized spin echo here, and then a small chemical shift difference delay and 90 pulse. And what you ended up with was this. So back in the day, this was much more popular. These anti-phase patterns were essentially diagnostic for the fact that he had generated a singlet order. It was done on this molecule here. You can see it's a very terrible molecule, actually. This is not something you want to do chemistry with, very toxic, but it has a very significant chemical shift difference. And in 2004, we were able to show that you could get a very long-lived order this way. And there's another type of experiment which doesn't apply strong and rapid spin locking. Instead, it's imposing symmetry by slowly cycling the field. This is the B0 field to 0. So in this, again, to some approximation, to a lot of approximations, let's say you have a perfectly adiabatic process where you remove your B0 field, and since your chemical shift difference is proportional to that, that goes away. Then your eigenpopulations should remain unchanged before and after the transformation. So let's say I start with this operator and pay attention to the notation here. This is the singlet precursor order. I go to low field, and it turns into singlet order, simply by virtue of adiabatic field cycling. We can say that these are adiabatically correlated operators. And you can even call this adiabatically correlated singlet order. And this was actually the very first singlet NMR experiment proper. And this, again, was done in an AX spin system. So this diagram actually doesn't make it very clear what's going on, so I've made my own. So what's going on here? And again, it's very intuitive to analyze in, let's say, the population space or eigenpopulation space. You start out with your normal Zeeman order. This is your Zeeman polarization. You apply this sequence, which basically accomplishes a selective inversion. So now instead of I1z plus I2z, let's say, you have I1z minus I2z. It corresponds to something like this. So I've moved this population difference, this polarization, into this kind of population difference, the zero quantum population difference. But because these are populations and they're not coherences, this is an eigenorder. And what I can do is I can move from this regime where I have this AX spin system. I can slowly remove the field, go to zero field. My chemical shift difference slowly disappears. And now my eigenbasis is no longer this Zeeman basis. It's turned into this singlet triplet eigenbasis. And these populations are carried over. So the population excess here turns into a population excess of the singlet state. Population deficit here turns into a population deficit of the T0 state. And what happens is you get rapid relaxation in the triplet manifold, but slow relaxation from the singlet state to the triplet state. And this is in direct analogy with the very well-known intersystem crossing processes, let's say in electron spin systems, which are responsible for things like phosphorescence. And let's say when you go back from a low field to high field, again, your populations are preserved. Whatever population excess you still have in this slowly relaxing singlet state, it's now going to go back to alpha beta. And then you can read this out. And this was what the data looked like in the very, very first paper, which started the field of singlets NMR. Again, you have these antiphase patterns, not very intuitive, not very welcoming to, let's say, a lot of spectroscopists. And it was on this dibromophenone spin system. And let's say one of the extraordinary things about these two experiments in 2004 is that they proved, despite the fact that a lot of people thought about this, but never did the experiments many years ago, it proved that you could just take ordinary room temperature magnetization, and you can turn that into exceptional long-lived spin order. In the simplest case of these two spin-half systems, even in the cases when you had a system that didn't have inherent molecular symmetry, like a parahydrogen, for example. And one of the problems is these first two sequences were designed for the extreme case of AX spin systems. They weren't general. And for a long time in the field, it was actually a problem that a lot of groups have been working on. To have sequences that convert magnetization to singlet order efficiently in a wide range of inequivalence regimes. So let's say when my chemical shift difference is almost non-existent, when it's on the order of the J coupling, what happens? And another problem with these sequences, which today we don't like very much, is that these sequences were asymmetric with respect to their generation and readout sequences. So going back here, you can see that what he used to generate the singlet order, or sorry, generate the singlet precursor order, is not what he used to convert it back to magnetization. And this makes things more complicated, leads to these complicated spectra. And now the big question is, how are you going to get singlet precursor order and singlet order from magnetization and vice versa? And that's been answered a lot in the past 10 years of work and research on the topic. You have all kinds of work by all of these amazing groups. You have the soft RF methods, like the slick method pioneered by Matros and Stephen DeBent. You have shaped RF methods, like adiabatic slick by the Warner Group, ABSOC by the late Konstantin Ivanov. You have hard pulse methods like the Sarkar sequence by Jeffrey Bodenhauser's group, Stephen Kadlicek, the ADAPT sequence by Gabriele Stevenotto. You have the echo-based methods like M2S and GM2S, which I'll talk about in a bit. GCM2S, which actually Stefan Glogler's group published at the same time as us, so credit goes out to them as well. There's optimal control optimization, again pioneered by the late Konstantin Ivanov, as well as other groups. There are more exotic methods, which I'm not such an expert in, such as fast field sweep methods and exploiting level anti-crossings. And there's direct hyperpolarization. And hyperpolarization is something I won't talk about at all. So, for example, this is a graph of one of the simplest, very simple singlet anamorphous sequences, which is SLIC. And you can see the efficiency of SLIC at preparing a singlet order as a function of your singlet triplet mixing angle. It works beautifully in the case of near equivalence. It still does a damn good job in the case of intermediate equivalence around here. But let's say as soon as you start getting a huge chemical shift difference, it doesn't work anymore. Which makes sense. A lot of these sequences were designed for the extremes. It's either strong inequivalence or strong or near equivalence, and the in-between cases started getting looked at later. And let's say I'm going to look at the sequences that our group has worked on for the sake of time. And we've made these two lovely sequences. There is GM2S, that's generalized magnetization to singlet. And this does the wonderful thing of converting your ordinary magnetization to singlet order for a wide range of these inequivalence regimes. There's another sequence we made, which is Gs2p. And this actually does something else. This takes the singlet order that you've made and it converts it into singlet precursor order. And both of these sequences are echo-based sequences. They're based on repeated trains of synchronized 180-degree pulses. And the reason behind this wasn't just for aesthetic. This is because with 180 pulses, it's so much easier to compensate against errors like resonance offset and let's say pulse inhomogeneities. So you can work against experimental error. And this is the GM2S sequence and its efficiency as a function of your singlet triplet mixing angle. And you can see that it accomplishes a good efficiency all the way up to 67.5 degrees. And these dips you see, with numeric optimizations, you can get rid of them. But let's say this is just with the analytical expressions, which I attach here. They're very bulky. But moving on, the Gs2p sequence, it's a complement to GM2S. It basically takes your singlet order, converts it very efficiently to singlet precursor order within the same range. So from 0 to 67.5 degrees. And the way it's designed is you basically have these nested echoes. You have this inner spin echo loop. Then you have another 180 pulse, an outer 180 pulse, and you have an outer loop. Let's say when you get these parameters right, you're going to get very good conversion of your singlet order to singlet precursor order. And let's say this is the scheme we had for actually testing our ideas. And it may seem like a very convoluted scheme, but it's very simple. The first thing you want to do is you want to equilibrate or polarize your system. And for it to return to thermal equilibrium, we have the singlet purge sequence at the beginning. And what the singlet purge sequence does is it eliminates all of this residual long-lived singlet order. So usually you want to wait 5 times T1 and not 5 times TS, especially when your TS is 1,000 seconds. So this saves you a lot of time. It also makes for a cleaner experiment. T00 filter we're talking about is literally just a gradient-based filter that eliminates anything except singlet order. So in a way, this T00 filter, think of it as remove everything except what's a singlet order. It's actually more complicated than that. In recent years, we figured out that there are a lot of problems associated with these filters. But let's say you have these steps going on. You have GM2S, you make singlet order. You purify that singlet order by removing all of the other extraneous elements. And you take that purified singlet order and you convert it to singlet precursor order. And this is a very clever step, actually, because singlet order has this T00 spherical tensor symmetry, so you can filter it. Singlet precursor order does not. So it wasn't obvious for quite some time how you could purify this precursor order until we came up with this intermediate step. So the first step really goes from magnetization to singlet precursor order. And then you can do a lot of things. You could either measure it at high field, you could either evolve its high field, or you could go to low field adiabatically and convert that to singlet order, which is indeed, we did both in our experiments. You can let it evolve at low field, then go back to high field. And the readout sequence here, this is again what everyone does nowadays. Instead of coming up with something ugly with anti-phase magnetization, no, it's just the time reverse of the generation sequence. So I go from a M to P magnetization to singlet precursor order, and then I go from P to M. And this M is actually Z magnetization. So what I can do is I can apply a Z filter. Again, there's a lot of filters here, but it makes for a cleaner experiment. This is how good practice is done, as we've learned over the years. And after the Z filter, you apply a 90-degree pulse and you're quiet. And this is the experimental setup we use for field cycling experiments. So it's basically a diagram of our magnet. You can see here there was this guide tube we had. And in the middle here, there's two sets of coils. There's a set of transverse excitation coils. This is when you could say irradiate your spins to low field. You could extend the lifetime of singlet order by decoupling some other relaxation mechanisms. But more importantly here, there's a set of shim coils, and this keeps a homogeneous magnetic field, let's say within the sample volume. And the shuttling is accomplished by this dynamo rope and a motor. So the motor pulls it up and down, and everything is programmed in topspin. And the model systems we used were these. So in this molecule, which is a derivative of a 13C2 labeled acetylene dicarboxylic acid, if you had dimethyl acetylene dicarboxylic acid, and it was deuterated on both sides, you'd obviously have no singlet triplet mixing element, and you'd have a system which was A2, your theta would be 0. But if I instead go from methyl-methyl to methyl-ethyl, what you instead get is the small singlet triplet mixing angle, which is enough to access singlet order. And I can actually build up this pattern logically. So I can go methyl-ethyl, methyl-isopropyl, methyl-tert-butyl, and in a controlled fashion, and let's say predictable steps of 20 degrees, I can control what a singlet triplet mixing angle I get. Of course, in the real world, this happens in reverse. You get a system, and whatever parameters it has, you're mostly stuck with it. But another thing here is you'll notice is that we've used deuterated substituents. And this turns out to be important because deuterons are less magnetic. And let's say proton out of pair dipole interactions are really going to influence the singlet order here. We want to keep this 13C2 singlet order as long as possible. So deuterated is. And here is just the parameters of these systems at 9.4 Tesla. you can see as expected, J coupling is very fixed. There are very few things that are going to change your J coupling dramatically, at least not in light nuclei. And you can see this inner splitting here, C, from which you can extrapolate the chemical shift difference. You can see the exact single triplet mixing angles here. That's actually not hertz, that's supposed to be in degrees. And this is essentially the mean chemical shift of the spin pair, which doesn't really follow any kind of pattern. But essentially, we prepared all of these systems in Shigemi tubes. Convection compensation is very important for long-lived order. We degas them extremely well. Let's say when you're doing this kind of NMR, the general rules or common sense that you've learned about just do 2 or 3 free-spot cycles and that's it. Generally, that's not enough anymore, and you'll see why in a bit. But here's just the spectra of these systems. So this is molecule A, the deuterated or per-deuterated methyl-ethyl ester. And this is your simple 90-degree spectrum in gray. And below it is your singlet precursor filtered spectrum. So this is after applying all of those pulse sequences here. And back again. And this is how much magnetization you get back. And we repeated that for here, this per deuterated methyl isopropyl ester. And finally, for the most inequivalent of these asymmetric diesters. And what I'm really trying to show here in these 3 pictures is 2 things. One of them is that with this kind of approach, you preserve the same line shape as normal magnetization. So there's no, let's say there's no disturbing patterns and antiphase and all of that. No, this is just simple magnetization. And another thing is you can see the efficiency. So it gets a lot of your magnetization back. And the theoretical maximum, let's say if we're going from magnetization to singlet order and back, is only a maximum of 2/3, 66%. So what we're getting here is very near the theoretical maximum. And here are just some brief notes about a singlet precursor order. So in the case that you have a very small symmetry breaking term and your singlet triplet mixing angle converges to 0, then obviously your singlet precursor order, yeah, it's not different from a singlet order. They're the same thing. They converge to each other. There's another distinct thing which has been overlooked by some, which is when, even if you're not doing field cycling, at fields where you have a significant symmetry breaking term, then the singlet precursor order is a long-lived operator in its own right. And it's distinct from singlet order. I made a typo here. And let's say that the relaxation of the singlet precursor order can be described with the time constant T lambda. And you can actually measure it separately from TS. And it's only with the TS that you're going to require something like a strong spin locking. But for the singlet precursor order, it's actually a long-lived eigenorder, even outside of the context of field cycling. Here's an example of what we did. We generated the singlet precursor order at 9.4 Tesla in these systems, and we monitored its decay. You can see you get these very nice mono-exponential curves. And in the intermediate equivalence regime, you also get these very nice mono-exponential curves. And this is very nice because let's say if you were to generate a singlet order, which is not an eigenorder in these systems, which are very inequivalent, then you would get all kinds of crazy oscillations. And in general, you wouldn't get a decay that was mono-exponential. So these are the parameters that we measure, like let's say by doing a range of relaxation experiments. There's your T1, which has a fairly predictable relationship here. There's your T lambda, which is more interesting. It goes from 44 seconds in the most, or the system closest equivalence, and then it reduces to 23.7 seconds. Whereas for the singlet order proper with spin locking, and this is at the same field, you get a different behavior. So in this very inequivalent system, for example, the singlet order has this long relaxation time of 50 seconds, which is significantly longer than a T1, while T lambda is only about twice as long as T1. In the near equivalence case, they're almost indistinguishable with an experimental error. But in intermediate equivalence, you get these strange effects. And again, what you can do is you can take the singlet precursor order, and you can do what it was designed to do, which is take it to low field, adiabatically, hence converting it to singlet order proper. And what you end up with is these insanely long lifetimes. So we measured, for example, using these different techniques, TSs of basically over an hour and 50 minutes for both the per-deuterated methyl-ethyl and methyl-isopropyl esters. Whereas in molecule C, it was below an hour, it was more like 45 minutes. It was still extremely impressive. And let's say T1 in these same conditions, that's with field cycling to 0.94 millitesla, is actually much shorter. It's on the order of 30 to 40 seconds. So that's 2 orders of magnitude, and that opens whole avenues for a new kind of magnetic resonance. And these are just correlation times, which we've measured or we've extrapolated not just based on the calculated dipole-dipole coupling between the 13C2 spin pairs, but also accounting for J and isotropy. So that's the second rank J coupling, which can act as a perturbation or an addition to your dipole coupling and causes this dipole-dipole relaxation for T1. But let's say what happens when you generate singlet order versus singlet precursor order. It doesn't really make a difference for near equivalent systems. It becomes important, however, for these intermediate inequivalent systems. So for example, in this system here, if I make the adiabatic precursor, I get this lovely decay, nice and clean. If I don't do that, I get this instead. So I have all these crazy oscillations, and it's less neat of an experiment. Of course, if you're a very good research group, like other research groups are, you can actually monitor these oscillations and look at these things at a low field. But in the interest of time, and especially for something as long-lived as this, you really want to do this additional step of converting it to the adiabatic precursor. And when you look at the most inequivalent system, you get something very interesting. We didn't see much of the oscillations. Maybe we didn't sample finely enough. But what you did see is that with this additional step of converting it to the correct precursor order, you preserve much more magnetization. Whereas you lose half of it immediately if you just do M2S. So this additional step, this additional pulse sequence really is crucial. And, just to go over my brief talk, we went over some of the basics of the field, the basic principles, the basic experiments, and we demonstrated some new sequences for generating both of these interesting operators beyond these approximations of, let's say, strong and weak inequivalence. And in the process, we accidentally discovered these new molecules which support this super ultra long-lived order beyond an hour in solution. And hopefully this will inspire some applications in the field, especially to more of these systems that don't satisfy these extremes of inequivalence or near equivalence, and that a lot of us would previously consider unsuitable for singlets NMR. And yeah, I'm ready to take questions.
Okay, nice. Thank you very much. This was a very interesting talk. So please feel free to ask your questions in the Q&A window. Just in order to give some time to the audience, maybe I can make the first question. So I was wondering, in these sequences that you showed, which are quite broadband over the range of theta, your loop counters are always the same for every case of theta, or you have to optimize it? And if you have to optimize it, how would you do that?
Oh, it's highly system dependent. So let's say, for example, for the GM2S sequence, then the smaller your symmetry breaking term, like the smaller your chemical shift difference or out of pair J coupling, the more loops you need. Because what you end up doing is you're amplifying a tiny term.
Mm-hmm.
So in some cases, when you have like a J coupling of 200 hertz and a chemical shift difference of just 2 hertz, then you might end up going to 100 loops or more. So it becomes more of a taxing sequence, uses a lot of power, a lot of heating.
Yeah.
But for the intermediate equivalence, this is going to be like 2 or 1.
Okay, so do you compensate for the power dissipation, or like is it heating up a lot your sample if you do a lot of loops?
So luckily for us doing liquid state NMR, that's never really a problem. So we never really experienced heating problems with these long loops. The problems you do experience tend to be when you're doing spin locking. So strong spin locking to basically suppress the symmetry breaking terms. Yeah, that tends to be the big killer.
So there is one question so far in the Q&A from Raj, asking, what do you predict would be the challenges involved with trying to achieve long-lived singlet order for the following scenarios? 1, solid samples, 2, samples with paramagnetic centers, and 3, samples with cluster radicals.
So for the first question, that's a very good one, because it's one that I've been interested in myself. And it's one which a lot of people have basically pursued unsuccessfully. Now, singlet triplet transitions in solids were well known for a long while, since the seminal paper by American Watt, where let's say they looked at these, I believe, diammonium oxalates in solids, and they had this very nice example. This is something which is an incoherent mechanism in liquids, but it's coherent in solids because you see everything. When you have 2 spins, and even if they're chemically equivalent, let's say they have the same isotropic chemical shift, they can have chemical shielding tensors which point in opposite directions or different directions. And as long as you have different directions that the principal axes are pointing in, you basically create this cross term with the dipolar coupling that acts as a symmetry breaking mechanism. And that can create these pseudo AB or AB patterns that you observe in solids. But to my knowledge, no one's used that to generate singlet order yet. And this was also seen in a lot of solid state NMR, like these 31p spin systems. And McDowell did a lot of work into that as well in the 90s. But let's say when it comes to our field, coming from liquid state NMR, for most of the time, people were really interested in these proton spin systems. And proton systems are lovely to work with in liquids. You have small, tiny J couplings like 10 hertz. But in solids, it's a total nightmare. I mean, how are you going to get rid of the dipolar coupling? how are you going to, use that tiny term, 10 hertz, to stabilize your singlet order? So the main challenges, I think, is if you want to do it in solids, and it's not even clear whether it's going to be long-lived, is you need to have, or you need to look at heavier nuclei. You're going to have to look at something like 31p, or maybe mercury, or maybe tin. You need to find a nice two-spin half system. You need to be in this regime where your dipole couplings are not very large. Your J couplings are huge, they're in the thousands of hertz. And you can also get a fast spinning and a good signal. So I think that's hard. And let's say most of us who are experienced in singlets and more don't know a lot about solids. For the second question about paramagnetic centers, yeah. So singlet order does not like paramagnetic centers. If you add paramagnetic impurities, it becomes short-lived, and we go to great pains to get rid of that. So we degas very carefully, we purge with HCl and so on, and yeah. So they can be still longer than T1, but they're not always very compatible. You're always going to reduce your lifetimes. And for clustered radicals, I'm not sure how to answer that question. Do you want to elaborate more?
Yeah, maybe Raj, if you want to add an additional comment, please feel free to do that. In the meantime, I had also another question about the sequences. Are you using usual hard, short 180-degree pulses, or to compensate for off-resonance effects and other problems like that, you use composite or adiabatic, and how short they should be in principle? Like,
that's also a good question. One of the nice things about 180 pulses is not only are they robust by default, but you can also add more robustness. So one of the techniques we like to do is we add composite pulses. So this doesn't even have to be crazy. It can just be 90, 180, 90. That compensates against the field of homogeneity. If you're worried about resonance offset, you can do something like the Shacopine sequence 60, 360. And they couple very well to these pulse sequences. And we just use simple 90 on 80, 90. Another thing you can do is you can add super cycles. So the traditional thing to do is you can add this 0022 super cycle. So just within a certain loop, especially when you have a system which uses a lot of them, that's what you do. And when it comes to the length of these pulses, it depends on how large your J coupling is. So for proton spin systems, for the experimental mutation frequencies that you use, let's say 10 microsecond pulses for a 90 degree, it tends to not matter, because your J couplings are tiny, and no matter how long your pulses get, they're never going to mess with these very sensitive tau1 delays. For heavier nuclei, it's another story. So when you have a J coupling of 200 hertz in carbon or 600 hertz in phosphorus, you need to be very, very careful about these delays, because if your pulse gets slightly longer, now you have to readjust it.
yeah, nice. And yeah, maybe there is another question from John Price. What are the challenges to do something similar to the experiment you just described, but with protons? Also, how long does it take to shuttle to the lower field?
So with protons, in a sense, it's a lot of less challenges. So in the beginning of a singlet NMR, we really looked mostly at proton system, and it's only later that we started playing with 13C and 31P. And unfortunately, often with these heavier nuclei, things get more complicated. With protons, things tend to get simpler. The pulse sequences are more forgiving. less sensitive and narrow with regards to these delays. You have much more polarization. You can have very dilute samples. What you can have as a challenge is with these small J couplings, they might not work, or they might be more sensitive to errors in certain sequences. So going to something like SLIC, for example, when you have a J coupling of 4 Hertz, you need to generate a nutation frequency of 4 Hertz, which is very, very hard unless you know what you're doing with your equipment. And when it comes to the length of shuttling to the lower field, it really depends. So with our shuttle, we tend to, or we used to have 6 or 5 seconds. And we said that's okay because we only had a string set up, basically, a tube on a string. But with our new shuttle, we can go down to, let's say, 500 microseconds. Or sorry, 500 milliseconds. Sorry, that's the wrong time scale. Yeah, and you can go relatively fast, and it's still relatively adiabatic. So the concern is not so much how slow you go, because you can always be slow. But the difficulty really is with relaxation. So if your shuttling is taking like 15 seconds and you have something which isn't very long-lived, that's going to cause a problem.
Also, Raj made an additional comment: by samples with cluster radicals, he meant by cluster radicals, I mean, if you have clustering of paramagnetic centers, which I guess is similar to the previous.
I'll have to say I'm not the best person to answer this question, because my job has basically been to remove all of these paramagnetic things. So to me, yeah, this is sacrilegious, and I can only remove paramagnetic centers. I can't have them. Yeah.
So how do you do the degassing usually?
The degassing, we use a freeze pump procedure. So the key here is that it's done for several cycles, much more than most people would consider sane. And let's say we use J-Young tubes. We freeze them. We leave them under vacuum for a while. We close the tube. We repeat this tediously over and over again, maybe 10 times. And at the end, you might pump in some argon, very pure argon gas, just to keep your tube sealed. And it's going to stay relatively stable for the next few months.
Okay, yeah, it sounds a difficult job, or at least repetitive, yeah. So we have another question. What would you expect about its real applications? Sorry if I missed it.
Yeah, with real applications, really, since the beginning of my talk, it's hyperpolarization. So to preserve your hyperpolarization, you need something which is long. And at the moment, our stuff is too short. And a lot of different groups are working on different techniques, but our area is long-lived spin orbit.